Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, this is part 3 in the Amiga 3000 repair series. This machine has really sent me down a rabbit hole. It all started in part 1 where this computer was freezing. So I think I fixed that with some deoxit in the sockets, but then I was getting this yellow screen of death. Well, it turned out, there were many comments on this, that the Amiga 3000 doesn't actually work without the riser card installed in the motherboard, which is weird to me because the 4000, which is a computer I've worked on before, that doesn't require that. And I've never worked on any other computer that has what looks like a passive riser like this that has to be installed for the computer to work. But what really threw me for a loop on this machine is that certain versions of Kickstart, notably 1.4, which are burned into some chips, and a super Kickstart version of 1.3, which is a disk loadable version, those work perfectly fine on this computer without the riser. You can run games and software and whatnot without any issues. It's only 2.0 and 2.04 that don't work. So in part 2, with the help of a new diagnostic ROM called AmigaMon, which I've worked on with a viewer, I was able to sort of see what I think is causing it to not work without the riser installed, at least with these later Kickstart ROMs. But here's something really interesting. I'm going to turn on the machine and I'm obviously holding the riser card. It's not installed, and this motherboard is totally bone stock and not modified in any way. And notice we are booted up, and this is actually running Kickstart 3.1 and Workbench 3.1, and it's working without a yellow screen. So in today's video, I'm going to show you exactly why the Amiga 3000 does not work with this riser not installed with Kickstart 2.04 and 3.1, and I'll show you how to bypass it. And then I'm going to try to get to, well, the final stages of this machine and trying to fix up the clock battery damage area and potentially get the flicker fixer working as well. Although I don't know how that's going to go, so that may or may not happen in this video. So without further ado, let's get right to it. Let's start off this video by exploring this yellow screen of death that the Amiga 3000 was putting me through before I figured out what the problem was. And let's try to get to the bottom of exactly why it happens. I like to answer those why questions. Like, I hate not knowing why things happen. And I want to know why this machine specifically gives us this yellow screen of death when the riser card is not installed in the board. So we're going to start off with Kickstart 2.04 ROMs. These are the actual chips that were in the machine when I first started working on it. And I'm going to be booting up off this floppy drive, Workbench 2.05. Actually, I'll take the disk out of the drive. So when we turn the machine on, which I just did, we don't get the yellow screen of death. It very quickly goes to the full white screen, and there we go. Kickstart 2.0, which is version 37.175. So if I put this disk in the drive, it's going to start booting, and yeah, this computer appears to work properly at this point. There's nothing special happening here. I'm not using the super Kickstart with the beta version of the ROMs. This is just the regular 2.05 Workbench disk that'll work on any Amiga that's got the Kickstart 2.0 style ROMs. Or you could even run 3.0 ROMs or 3.1 ROMs and still run this floppy disk. So there we go. System is booted up. And we do have all of our RAM available to us. And we can tell one thing by the amount of memory listed here is we know this machine has 4 megs of fast memory. That's over here on my right hand. And then we have 1 meg of chip memory. Well, with the Super Kickstart, which is what you need to do when you have the beta version of the ROMs, it basically loads the Kickstart off a floppy disk, puts it into fast memory, which is this RAM here, takes 512K of it, and the CPU memory management unit remaps that to act as if it's the ROM chips. Access time to the RAM is a lot faster than it is to the ROMs. ROMs are kind of slow. So doing that caching, that 32-bit caching, speeds up the system quite a bit. Well, we'd be able to tell by just the free memory here if it was caching or not, because we would have 512 less K of RAM, and we're getting basically all of the RAM available to us. We can switch over to sysinfo, and we should be able to tell also if the RAM is being remapped. So right here, MMU not in use. And if we go to memory, we can see that we have a full 4.0 megabytes of RAM available. If the MMU were in use while it's caching the ROMs into the RAM, doing the shadowing, we would have 3.5 megabytes of RAM available to us. Either way, the real demonstration I wanted to do is if we just pop the card out, I'm just going to show you again, because the last video was very long, and in case you hadn't seen it all, wow, it's really hard to get this card out of here. We pop the riser card out. Now, if I turn the machine on, it's very quickly going to give us, yes, there we go. We got the yellow screen of death, and the computer will just boot loop at this point. In part 2, I showed off the new Amiga Mon diagnostic ROM, and that actually kind of shows you what's happening during the initialization phase. And we replicated what the Kickstart ROM is doing as the system boots. And at some point, Kickstart ROM checks to see if there's any Zorro 2 expansion cards installed. And if there is, it needs to run the code that's in the ROMs on those cards to kind of auto-configure them and stuff like that. It looked like the difference when you have this in or not in is that any kind of probes to the Zorro 2 auto-configure RAM, that's part of the system that's used to auto-configure the plug-in cards for the Amiga 2000 and 3000 and 4000. When the motherboard's in a specific configuration and this card is not installed, a bus error is generated, which is actually a hardware flag that goes to the CPU, which causes an exception. An exception on a processor is anytime something happens, like an error of some kind that was unexpected. Now, typically when an OS is running, you have an exception handler that's installed, and these are vectors that get run when the exception fires. Each vector is a location in memory that the code can jump to handle the exception. Even something like an interrupt, an IRQ, that causes an exception. So you have to have an exception or an IRQ handler set up with a vector pointing to it so that the processor knows what to do when an interrupt comes in. Well, a bus error exception is typically a hardware fault, like there's something wrong that causes a bus error. So a lot of times, most computers will just sort of crash and will print a message that says bus error, you got to reboot. And even the Amiga Workbench, once it's running, it does that. Guru meditation with a flashing message. I think, I can't remember the code. It shows some codes when it pops up. One of the codes specifically, I think it's like a B, maybe 80000 and a B at the end, or maybe it's an F at the end. I can't remember which one it is, means bus error. So that Guru meditation would pop up, and you press the mouse button and the system would reboot. The problem is when the system is in its initialization phase, while it's still initializing the hardware, that's the gray screen, there is no exception handler other than change the screen to yellow and then reboot. So any exception that comes up during that phase, no matter what it is, will just make the screen yellow and the system will reboot. So I think what I'm going to do right now is I'm going to revert this machine back to the version 1.4 ROMs, which are the beta ROMs that use the Super Kick, and I'm going to run the Amiga Mon diagnostic, the latest version, and we can kind of look at what this machine is doing when it boots up without the riser card installed. And the main reason why I'm doing this is because I still want answers as to why these ROMs work perfectly and can boot the system, and why Kickstart 1.3 also can boot the system perfectly, and it's only 2.04 or higher that seems to have this yellow screen of death issue. All right, Kickstart 1.4 is in the computer, and here is the updated disk that has the latest version of the Amiga Monitor Diagnostic ROM. With the riser card not installed at the computer, let's power this thing up. And we will have to do a soft kick to load the ROM image into FastRAM. Now, since part 2, we've actually done some more work on the diagnostic ROM. It's still really early days and not really capable of doing a whole lot yet, but the diagnostic process is a little bit more involved with this latest version, which we're calling version 8. And here it goes, RAM test, a little bit of chip RAM, and okay, there we go. So we got our bus error. And I know this is a wall of text right now, but look to number 18, expansion Zorro 2 autoconfigure E80000. That's the memory location where the Zorro 2 autoconfigure ROMs live, and that's what the Kickstart ROM, I think, is probing as the system boots. Now, under line 18, the next line says BERR mode. That's bus error mode, and it's talking about a configuration register. It's actually a single bit at a certain address that configures Gary to either generate a bus error if the CPU tries to access some of the memory that doesn't physically exist, or the other mode, if you have that bit unset, then what happens is Gary does not generate a bus error. And I think what it does is it just generates the normal DSAC signal, which is sort of a bus arbitration signal that goes to the CPU to say, yeah, everything is fine. And with the register set one way, it would generate a bus error. And with the register set the other way, where I had the bit set to a 0 and I tried to go to E80000, that same address, I wouldn't get a bus error and I would just see all Fs. And to demonstrate this, we just turn the power off and I plug the riser in. We boot the computer back up again and we'll redo the super kick process. There we go. It got past, the error, and there's a whole bunch more tests and stuff going on, but it actually finished. I don't have a keyboard connected to the computer right now, but what I have is PuTTY open and I have a serial port connected to this. So all of the stuff we just saw is also output through PuTTY. So this was the previous execution of the ROM where we had the bus error, and there's even a message now that says, make sure you install the riser to populate the 02 slots. And then when it ran again, it did not halt. So this leads back to the question of why does Superkick 1.3 and the 1.4 ROMs work totally fine, but as soon as we load 2.04 ROMs either on the board physically or with a Super Kickstart, it doesn't work. We get the yellow screen. And it all depends on whether this riser card is installed in the board or not. So going with the idea that this yellow screen of death is a bus error, that's an assumption we're going to have to make, and that it is probably related to access to the 02 memory space, that's another assumption we're going to have to make. What if we take a look inside all the various Kickstart ROMs and see which of them, A, fiddle with the register inside Gary to turn on or off the bus error generation, and then also which of the Kickstart ROMs actually take a look at that memory location that I think is causing our issue, the E80000. Well, the viewer who's been helping me make this diagnostic ROM for this, took up the task of analyzing all the code running in all these various different Kickstart ROMs and put it into a spreadsheet for me. And this is that spreadsheet. So over on the left in column A, we have various stages of boot, and it's pretty much top down. And we have all these different versions of Kickstart. So 1.3, 2.04, and 3.1, but this is all for the 16-bit versions of the Amiga. And then we have the Amiga 1200 version of Kickstart 3.1. And then we get into Amiga 3000, we have the Super Kickstart version, that's the 1.4 that's currently on this machine, 2.04, 3.1, and the Amiga 4000 version of 3.1. So specifically, things that are very relevant to us are any writes to the Gary configuration register that affect whether bus errors are generated or not. So there's that, and then there's also any accesses to E80000, that 02 autoconfigure space. If we take a look at the versions for the 16-bit Amigas and we scroll down here, here it is. This is it. The Gary plus TOE-NB register init, line 20. It's not even in these Kickstart ROMs. And of course it's not, because those ROMs are designed for machines that don't have this Gary chip. It doesn't seem to be also in the Amiga 1200 version of Kickstart 3.1. But if we look over at the versions for the 3000, we can see that, well, version 36, the 1.4 ROMs that are in here now, they don't touch that register either, but 2.04 and 3.1 do actually set that register to 00, at least at this phase in the boot process as it starts going up. And notice here it says color 0, dark gray. It scrolled over there, so yeah, dark gray or near black on 3.1. Now, what is curious is the Amiga 4000 versions of the ROM also set those registers. So the Amiga 4000 might actually have a Gary type chip. I don't know if it's called something else that also has the same register available to it. But none of the other versions actually do set that, including version 1.4, the one that's on here right now. And that's the one that we know has never done any kind of crashing, whether or not the riser card is installed or not. Now, if we keep going down through all the various steps that are happening, there are some differences between the version of the ROM that's on here now, 1.4. It's sort of missing a bunch of stuff, and it definitely got added later in 2.04. But look at this, step 41, Gary timeout to bus error mode flip. And the Kickstart actually writes 80 to the register at DE0000. Well, go back to part 2 and take a look. When I manually did that, and then I tried to access E80000 inside AmigaMon, we'd get a bus error. I actually wrote FF to that register, but it's actually the most significant bit in that register, which is bit 7, that sets that mode on or off. Well, when you write 80 to it, bit 7 is turned on, and when you write 00 to it, as it was up above, then it's off. And notice with 1.4 ROM, it says absent because there is no code in that ROM that ever touches that Gary chip at all. The Gary's in the default configuration, which probably is just 00 at power on. And of course, we scroll over, none of these other ROMs do that either because of course they don't have a Gary chip that has that register anyways. And oddly enough, if we look at the Amiga 4000 column, it also does not set that mode on Gary. If we scroll up, back to what is it, line 20, 20 and 21 right here, it puts 00 in that register. So it does set it up as 00, like as a power on thing, but it never changes it back to 80. That is only something that happens on the Amiga 3000. And I've heard anecdotally from people that the riser card does not need to be installed on the Amiga 4000 for it to work. And that could easily be the reason right there. And then when it comes to accessing 02 autoconfigure, there is no direct references in this ROM to it, but it is indirectly referenced inside expansion library. And the expansion library is resident inside the ROM itself. So unlike the 16-bit ROMs, which do have direct reference, like you can find a reference directly to E80000 in the code, definitely it's called inside the expansion library, which is inside the ROM on the Amiga 3000. And there is a direct reference on version 1.4 to that space, but of course the Gary chip is not in the mode which will generate a bus error, so it doesn't generate a bus error. And I think right here, this kind of clinches it. The fact that it's unique to 2.04 and 3.1 on the Amiga 3000 that sets Gary to 80 at this step right here, I think is what causes the yellow screen when the riser is not installed. Why did Commodore do it for just these two ROMs on the Amiga 3000 and it's not going to happen on the 4000? It's not going to happen on any of the other machines? I don't know. But this is definitely something that's unique to the software on the 3000. Now, to validate that this hypothesis is correct, what if we just patch Kickstart 2.04 on a floppy disk, one of the super kick disks, and change that write to the Gary register from 80 to 00. So we'll just write the 00 to it again, which will not enable the bus error. And then when the expansion library goes to scan the 02 config space, well, Gary's not configured to generate a bus error, and it should just work. So with one single bit change, well, you got to change a little bit more than that because there's a checksum routine on the Kickstart ROM as well. But just changing that single move command that puts an 80 into Gary and change it to a 00 and then fix the checksum, that should literally make Kickstart 2.04 work on this machine with the riser card removed. And I happen to have a Super Kickstart disk with the modified Kickstart on it. Let's see if that's actually the case. Haven't tried this yet. And what we'll do is we'll start with the stock Kickstart 2.04 that's on this disk here, and then we will go to the modified version. Okay, here we go. It's rebooting. We should get a yellow screen, and there it is, yellow screen. Okay, that's the stock Kickstart 2.04 ROM. This floppy disk here, it says Super Kick. This is the one with the modified 2.04 ROM on it. And let's see if this yellow screens. If not, it should just boot up into Workbench normally. This is once I go to the option here and load the Super Kickstart, and we'd have a working machine. And that's without the riser card installed. So we click floppy, and let's see what happens. And here we go. Here's the moment of truth. Look at that. It's working. That was it. That is, without a doubt, what's going on with Kickstart. And I just put the Workbench disk in there, so it's going to boot into the OS. So why did Commodore change that bit in Gary on the Amiga 3000 on Kickstart 2.0 and 3.1 to cause a bus error when the riser card is not installed? There is literally no other problem with the system. The computer will work perfectly right now without the riser card installed. This is not needed for the computer to work. Everything is functional on this machine without it. I mean, you'll see it should boot up. I mean, I haven't tried this yet. Yeah, here we go. It booted. And look, how much RAM do we have? We have exactly what I said we would have. We have 512 less K of RAM, and that's because, of course, we are using Super Kickstart, which means it took the Kickstart image off this disk here and loaded it into the fast RAM. If I just took that Kickstart that's on this disk and made some chips, then we wouldn't have that problem. We would have all of our memory available to us. So like I said, that's the answer why this machine was yellow screening without the riser card installed. Commodore, for whatever reason, in those two Kickstart versions, sets the Gary bit that if the bus is floating, it actually generates a bus error. Otherwise, the computer does not generate a bus error, and as you can see, it just works perfectly. Why did they do that? Why did they change it on the 4000? I have no idea, but that literally is why this problem is happening. Now, if you're having a yellow screen for some other reason, of course, I don't know. There's probably a different reason for that. But the other thing is, that Gary register could generate bus errors in other circumstances as well, like writes and reads to anything else that the Gary chip controls. And it controls a bunch of devices on the Amiga, so theoretically that bit being set could just result in a yellow screen for other hardware faults on the machine as well, which is not particularly helpful because a system that kind of works but allows you to see, oh, like this one piece of it is broken, then that will actually give you more options to do troubleshooting. The yellow screen of death tells you nothing. That gives you no information about what's going on because any exception could generate that same yellow screen, not just bus errors. For me, just knowing exactly why this machine was giving me the yellow screen of death is so helpful. And in fact, having the Amiga monitor loadable Kickstart now is also super helpful because if I have another machine, another Amiga that has other weird symptoms, then potentially booting that ROM will also give me a lot more insight, since all those diagnostic steps that you saw appearing on screen are really replicated from what the actual Commodore Kickstart ROMs are doing. And if you're getting hung up at some point in the Kickstart boot process, and for me personally, it's so helpful to be able to see exactly what's happening each step of the way and be able to kind of analyze what the error was and try to use that information to come to a conclusion. And with regards to the Amiga Diagnostic ROM version 2, that was the first one I tried on this machine. I think it was in part 1. That ROM worked perfectly on this machine. It didn't say there was any kind of problem whatsoever. So if anyone knows how to reach out to the creator of that ROM, because I don't think it's an open source ROM, perhaps they can add the Gary register reads and writes and then change it to the mode 80, which is the one that will generate the bus error when the riser is not installed. And in that case, they could print a message that says, hey, Amiga 3000 question mark, make sure the riser card is installed because you're getting a bus error on the Zorro 2 autoconfigure. I know if I had seen that message when I first ran the diagnostic ROM, that would have saved hours of my time and your time because you wouldn't have to watch me troubleshoot this. But on the other hand, I still think it's a good thing because we got Amiga Monitor out of it. And I hope that that's going to turn to something kind of useful or semi-useful for the community at large. Actually, before I try to fix the flicker fixer and the clock that's not working, I want to experiment a little bit and see if I can get this machine fully working with 3.1, Kickstart 3.1 that is, and boot it off of SCSI. I want to know if everything else on this machine works before I go ahead and try to attempt some more repairs, because honestly, I haven't tested that the SCSI works, and that was something I suspected, I think, in part 1 that might be an issue. And now that I know that a modified Kickstart ROM is all that's needed to have this thing fully work without the riser card, why don't we go ahead and see if that's the case. So just to show that this machine still is in the bone stock configuration, let's install Kickstart 2.04. This is these are the set of chips that were in this machine when I first started working on it. And let's turn this on. Yep, we got pin 1 in the correct direction. We should get the yellow screen of death. Yep, there we go, we do. So just as we would expect. And of course, we know that if I installed the riser card, then the machine would start to boot. So let's pop these 2 chips out. And I've gone ahead and I prepared a couple EEPROMs, and these are 27C400 chips. So this is the kind that I won't need to have a little jumper wire installed on. And let's get these in. This is Kickstart 3.1, and it's modified with that single byte change for the Fat Gary register that we talked about. And here we go. Let's turn this thing on, and let's see if this thing actually boots. Now, I did try this earlier just to make sure it did work. And it takes a while for this to actually start to boot. I think what's happening is that the BlueSCSI that's attached here is, well, it's scanning the BlueSCSI to see if it can find a suitable hard drive. There is a hard drive image on the BlueSCSI, but it's not initialized whatsoever. Therefore, let me just take the disk out of here that's in the disk drive. Therefore, it should eventually prompt us to insert a disk, and I have a GoTech installed, connected up to the second disk drive. It's in this Amiga disk drive case here. I'm going to set it to boot Workbench 3.1 off of that. But this takes a while because I think the BlueSCSI, like I said, is in there. And I'm going to keep this on there because I want to make sure that when we load the installer, that it's actually going to find a hard drive. So because I want to partition the image that's on there and get it all working. I mean, that's if, of course, SCSI is even working. And the difficult thing about Kickstart 3.1 is that it doesn't show you, I mean, if there's no problems, that is, it doesn't show us any status. It doesn't have like the gray screen. It just sort of has this slightly not totally black screen. And you might look at this and be like, oh, this is just not even working, right? But the disk drive just accessed, there it is. Yep, so there it is. So we're running ROM 40.062. I thought it was 40.62. Anyways, 3.1. And I'm going to set the disk here. There we go. I have installer 3.1 selected. And it is now loading, just balancing everything carefully. And as you can see, I mean, we kind of knew this already because I showed this off using the Super Kickstart disks, that with that single byte modified, the thing doesn't need the riser. This is not something that's necessary for the machine to operate. That's just a choice that Commodore made when they were creating these Kickstart images. Now, do I fully remember how to set up Workbench 3.1 and get the hard drive all set up? No. So let's just try HD setup And we'll see if this is able to detect that BlueSCSI. I mean, the SCSI might be broken for all I know. Partition the hard drive. Okay, set the hard drive as ID 0. And it doesn't have anything on it, it's just a blank partition. Let's see what happens. Actually, I mean, I think it might actually have something. It's like 500 megabytes or so. It was a Mac partition. I just copied the file. Could not partition the hard drive. Does that mean it could not find the hard drive? It's quite possible. I think HD Toolbox is probably the better tool to should have run this in the first place. It's been many, many years since I've done any kind of setup on an Amiga. And as I mentioned, this will be my first time ever trying to use an Amiga 3000, well, pretty much ever. Now, this does have an internal 50-pin cable or connection right here for an internal hard drive. Because I don't have that hard drive on the system, I went ahead and I installed termination resistors. So there's one here, and I think there are 2 more on this side of the connector. It's a resistor pack. I don't know if those are necessary for SCSI to work or not, but okay, well, I don't know. Is this working? Define new. Let's try reading the config. See if this actually is able to talk to the BlueSCSI. Doesn't seem like it is. Now, this might be something where I have to remove these termination resistors. Yep, this does not support the SCSI inquiry command. I somehow think that's probably not the case. I'm just looking at the BlueSCSI. It looks like there was a blue LED that's on, and it's not on at this point. Okay, wait a second. I think that's working now. So what I did is I edited the BlueSCSI INI. I didn't change anything on the motherboard. Still got the resistors. This is working, but I think 512 megs might be too much for it because we had an error there. And yes, awesome BlueSCSI is exactly what it's set up as. Can't find track size, assuming 68. All right, so I changed the partition down to just 100 megabytes, thinking that might help. And it's still giving me this weird error about track size, but at least it's showing up as 99 megabytes. So I think that's correct. Who knows? All right, so let's see if this works. So there we go. Awesome BlueSCSI 1.0. That's what we wanted. We know we're able to read the BlueSCSI, and I am just self-powering it right off the Amiga bus, by the way. So now we can partition this drive. I never really did the 2 partition thing on the Amiga. I don't know why you want to do that. So we'll just make one big one. Call this DH0. That is what I like. Bootable International FFS. That's the unreliable one. I know there's a better one. It's like Professional File System or something like that, but we'll just stick with the bone stock right now. Okay, there we go. So I think we should reboot the computer, and that theoretically should now allow us to see that, and then we can do the regular Workbench install procedure. Yeah, not a DOS disk. Yep, we know that. Why did it fail? Oh, it's trying to boot off of it. Okay, and that's because the boot order, if you hold down both mouse buttons, the boot order defaults to the SCSI drive. Before, the SCSI drive wasn't even readable, so it wasn't finding it. But yeah, so it's DF0, internal floppy drive, this one, and then the hard drive, and then the external drive. Well, we want to boot off this. So we're going to hit, because yeah, the priority right there, by the way, it's -20. So we're going to boot off DF2, and that should now boot this external drive and not try to load off the SCSI disk. Now, I know a lot of people in part 1 were telling me like, oh, you can hold down both mouse buttons for the boot menu. I mean, that only works in 3.1. I don't even think that's a feature in 2.04, although maybe it is. I can't quite recall, but definitely in Kickstart 1.4, that was the beta version that was on here, and 1.3 doesn't not have those at all. So what I can do, there's DH0. We can actually format that disk. We're just going to call it work, turn on the directory cache, and we'll do quick format. And yep. We're going to initialize disk. Should come up in just a second. Yes, there it is. Okay, cool. So now we can install this, and that will change the icon. Really what I'm just trying to do here is not create like the final system I'm going to use on this machine. I need to install utilities and stuff like that, but I just kind of want to show that this thing is fully functional, can boot off SCSI, is working perfectly without the riser. I mean, we already know that it is because clearly it's working. So now it's just a matter of swapping disks as it asks, and then I'll be right back. All right, there we go. The installation is done. You'll notice a hard drive icon changed. So we'll hit proceed. I think this should reboot the system. There's no disk in the first floppy drive. And let's see how quickly it boots up. Yeah, it's going already. I can see the light on the BlueSCSI booting, and yep, here we have it. So I can eject this extra disk. Oh, actually, you know what? I'm going to use this to copy a couple utilities on first. So I have degrader on here. I have no click on here, so it keeps the floppy drives from clicking. And we have sysinfo 4.3 as well. Now I know sysinfo, there's a 4.4 out, but I don't have a copy of that right now, so we'll stick with 4.3. So right off the bat, if we run this, looks like the Kickstart ROM is not copied into RAM, so we're not getting the performance benefit because it says MMU not in use. I am curious how fast our hard drive is, so let's do speed. Let's see how quick this is. I don't think, oh, 2 megabytes a second. Yeah, not bad at all. I don't have like the fastest SD card in here either, but that's quite speedy. Looks like we have these caches turned on. Data burst is not turned on. I don't know if that really makes a difference. Let's do speed. I think this is going to be underperforming because we don't have the Kickstart copied in. A3000, well, it got a 1.00 actually, so maybe that is okay. So if we turn off our caches and we do speed again, I think now A3000 will be lower, 0.70. Okay, so maybe this benchmark is not affected by having the Kickstart copied into RAM, actually. Someone had commented in the last video saying that it was the CPU command you could use for the Amiga 3000 to automatically cache the Kickstart into RAM. And I don't know what the syntax would be. Oh, okay, this is the cache stuff. So data cache, instruction cache. No fast-ROM S, fast-ROM. Okay, so that must be it, right? Fast-ROM. Okay, so does that take up the memory? Oh yeah, look at that. Our memory just dropped away. So that must be the command we're using to actually get our speed increase. So if we go on sysinfo now, we should see MMU in use. Yes, we do. And we're going to lose part of our memory. Of course, going to say 3.5. Oh, it still says 4.0. Interesting. But this is likely the command we have to put into our startup sequence so that we get the most performance possible from this machine, which I'm sort of remembering as I go. I'm pretty sure it's the startup sequence that's right here in the S directory. Now there is a text editor. I don't know if I'm going to be able to use it or not. Might have to install something a bit better. Oh, wait, this is graphical. Okay, so yeah, I can use this. Excellent. So now I just need to figure out everything I want to actually run here. So I know it's C:CPU. So I assume cache and burst are the instruction cache and burst, and then data cache and data burst are those. And then we're going to add fast ROM. Let's just make sure that that is actually the correct syntax. Yes, it took that. Okay. Actually, now I think about it, cache and burst probably turns on both data cache and instruction cache, because now I see data cache and instruction cache are separate. Now, the person who was commenting on this mentioned that this was actually run automatically or added automatically to startup sequence by the installer, but that didn't seem to happen here unless it's happening in one of the other files. Let's see if this actually forks over to another file. So it's making the RAM disk stuff, does some assigns. This is sort of like aliases of different drives and stuff. So like Deb's printers is a folder, ends up as printers : bind drivers, doing amounts, looking at some monitor stuff. Yeah, this is monitor related, set environment variables, add data types, iprefs, conclip. That's something to do with that. Oh, here we go, user startup. Let's check user startup because it might actually be in there. So we'll save that and let's open, oh, there is no user startup. Okay, whoops, that was weird. I thought I hit a cancel. Let's go back to that. Yeah, it's if exists user startup, then execute it. Otherwise, doesn't actually do it. Okay, well, what we should do now is we'll quit out of this, close all this stuff, and let's see when we reboot if we actually have our less memory from the ROM being cached. So control Amiga, and no disks or any other drives, so that's good. And let's see what happens. I can see the BlueSCSI flashing. There's our command. Oops, I forgot to save my backdrop here. So I think you do snapshot, window, all. I can't remember which one it is. We'll do both. But yeah, definitely our MMU is running now because notice this is less. If we check sysinfo, I really need to organize a little bit. Yep, MMU is in use. And again, memory shows 4.0, but it must be taking the memory from Kickstart's free memory table because it obviously would be closer to 4 megabytes there. without the ROM being shadowed into the RAM. All right, so this machine is obviously working perfectly. So stock unmodified Amiga 3000 can run without the riser installed as long as you modify a single byte in the Kickstart ROM, 2.04 or 3.1, and you will need to recalculate the checksum as well. Then you can use this thing with this in or out. Doesn't really matter. It's going to be either way. There's obviously no ill effects. The computer is working perfectly. Obviously, we can't use expansion cards, but putting this in, yeah, it will totally work. And it's just an arbitrary decision that Commodore made with these two ROM files for the 3000 that prevent it from working when this is in. My assumption is the 4000 is exactly the same because we saw the Kickstart table. They are not setting that Fat Gary bit to the same thing they were setting on this, which was 80. They left it at 00, which is now how it's currently set on this machine. I have a feeling if we modify the Amiga 4000 Kickstart ROM and change Fat Gary's register value to 80, just like on this, it probably will give a yellow screen of death when the Amiga 4000 riser is not installed. I haven't tested that. That may or may not be true, but it's just saying that it's likely that it's going to be the same behavior. And who knows why Commodore changed up the behavior between this one and the 4000, but they obviously did. Now, if you want to make this modification yourself to Kickstart ROM and then put it on some EEPROM so you can run your 3000 without the riser, well, there's going to be a Python script available to actually modify the ROM and recalculate the checksum for you. I will put a description of the Python script down below, so if you want to check it out, you can do so. So at this point, this machine obviously working really well, and what's actually left for me to do is get this clock chip, hopefully it works, back in the board, and then see if we can fix that flicker fixer. I'm going to fix that one trace and see if that makes a difference. If not, I'll probably have to break this out into a fourth video where I try to troubleshoot the flicker fixer in more depth because it's a pretty complex circuit that I don't really understand right now. So we'll see if I can get it working. Okay, the first thing I want to try to work on is this clock calendar situation. So far, that hasn't presented any kind of issue not working, but I'd like to get it on the board just so it's there. Now, this was the chip that was actually on the board originally. You can see the markings are pretty much not readable. It's a Ricoh something or other part. I don't have any spares, so hopefully this chip is working. I did sand the pins down using a fiberglass brush, so hopefully that was all it needs, and it is installed in a couple pin strips. And the reason why it's a pin strip and not a regular socket is I don't like the fact that when you put a socket in, it kind of covers up these traces that are in the middle of this socket. And of course, this has all had corrosion, and I want to make it easy to access those traces in the future if something seems to go wrong with corrosion. Now, one thing I did is when I cleaned up this board, I also removed a bunch of components from this area, but all the stuff that I took out was all to do with the battery charging and the power to this chip itself. So I'll just have to reconstruct that. And I'm going to use something like this, a CR2032 holder, to power this chip up when the machine is not running. And to do that, I have the Amiga 3000 schematics up. I am not going to be using a rechargeable battery, so I don't need to have any of this recharging stuff that's in here now. And this is the datasheet for the Ricoh clock chip. Now, pin 18 is the power input, and I just wanted to check what it needs for supply voltage. And it looks like, well, maximum of 7, but it does say down here, recommended is 5 volts with a maximum of 5.25, but data preservation voltage is the important part. Minimum is 2.2 volts. If I'm going to be using a 2032 cell, those are around 3.1 volts when they're new, and they slowly drop down. But the fact that it can go all the way to 2.2 volts means I think there'll be no trouble using one of those in this board. It might not last as long as one of those like 4.5 volt lithium cells, but I'd rather just use the common CR2032 anyways, because even though they can leak technically, generally when they leak, it's not destructive. It's just a little bit of corrosion, and that happens after many, many years. Now, looking at the little power supply circuit, I don't really get why it's hooked up to 12 volts, and then there's a 1N4148 diode connected to 5 volts. The power flows the direction of the arrow, so it goes down to the chip. It can't go backwards, so this line means any voltage is trying to go back this direction is stopped. So oddly, with the design that's sort of the stock configuration, 12 volts comes through a 470 ohm resistor and goes through another diode to the 5 volt rail. Why? So I think what I'm going to do is I'm going to rework this. I'm going to remove this resistor entirely. It's going to disconnect the 12 volt rail. I'm going to swap this diode around, and I'm going to put a diode down to this junction point. I'm going to remove this resistor, and then I'm going to add another diode that goes down to the battery. So like this. And that means that power from the battery can flow into the VCC pin of the chip, but it can't go the other way. Sorry, that's multimeter timing out there. But the 5 volts that comes down can't go into the battery. So essentially, this can feed the chip or this can feed the chip. I did take out C190. I'll have to put that back, 4.7 microfarad. C191 is still in the board. And as I said, I think this gets removed. And this, of course, is already gone. Those two are gone from the board, and I'm just going to cut that resistor. So 2 diodes, the battery holder, and reinstalling C190, and of course reinstalling the chip in those pin strips. And I think that'll be the trick. I don't know if this chip works. I don't have a way to really test it. So if we put this thing in and the Amiga OS can't communicate to it, then I guess the chip is bad, or maybe one of these other traces that go to it are bad. It only communicates on 4 data bits, and then there are address lines. The address lines go to this little latch, and then the data lines, I think they are just directly on the same data bus, yep, as the ROMs and stuff like that. And then the oddly named fail input on pin 2, this is the chip select line. I don't know why it's called that specifically, but I think that comes from Gary or one of the other chips. And then the alarm pin is not used. And the fail line actually is not just a chip select for that. What is a PST518? Is this like a little voltage reference just to check to make sure the 5-volt rail is actually working properly? I bet that's exactly what that is. I think what that means is the clock chip is selected anytime the 5-volt rail is correct, but it's not reading and writing to the data bus because it needs either the read or the write inputs coming to it. Some chips work in a different way where they have a single pin that's either read or write, so it's either reading or writing from the bus, and therefore you need to have an active chip select line that only turns on when the chip is accessed. But this clock chip has independent read and write inputs. So hopefully that makes a little sense. And luckily this has the notch still visible in the silk screen, so I know that the notch goes that way, facing that direction. Let me get this stuff soldered in, or at least I'll get this chip soldered in, and I'm going to hook up some of the components as I mentioned and try to get this all wired up so we can see if this chip is working and there's no actual damage here. If it works, then what I'm going to do is there's no paint or lacquer on top of this exposed copper. So once that is the case, I'll take this chip out and I'll put lacquer on all of this stuff here, and then it will be preserved and not exposed to oxygen under the clear nail polish. Same goes for the exposed traces that are underneath these 2 chips. They're also in pin strips. I did that, I think, in part 1. And that means I can paint the nail polish on there pretty easily, cover up those traces. And I think the only other damage that we're going to have to deal with in this video is potentially a bad trace up in the flicker fixer area. That's, of course, if the clock stuff works and the chip's not bad. Okay, this is what I've come up with. So the battery holder is attached. This diode goes from there, which is 5 volts, over to this point, which is pin 18. That feeds the VCC of the clock chip. I put a new 4.7 microfarad capacitor there between pin 18, just kind of this junction point right here, and ground. And then there is a little bypass cap as well installed. This is ground over here, and that's that same junction point. Or sorry, it's this bypass cap right there. So that kind of restores the power supply coming from the main power. Now, when it comes to the battery itself, the positive side, which is this side of the battery holder, this side is for negative, it's just hooked up to the flood fill. On the bottom side of the board, we have a couple bodges. So this bodge right here is actually for the negative side of the battery holder. It was just very corroded, so I wanted to add an extra little offcut that goes over to this flood fill here, which has a good, nice, solid ground connection. This is the positive side of the battery. It was no longer connected because the traces were all corroded, not to mention I think it went to this junction point right here between those resistors and stuff like that. So this is a Schottky diode, which feeds the 3.1 or 3.2 volts from the battery holder over to the clock chip. It's just going directly through there, right into the clock chip. But of course, the 5 volt from the power supply on the top side of the board can't feed its way back into the battery itself, so it can't charge this battery. And also, because there's a regular diode, 1N4148, on the other side, the battery voltage itself also will not make its way to try to power up the whole motherboard. You won't find the battery voltage on any of the components on the motherboard. Now, if we flip this back over and we put the battery in, we can kind of give this a little bit of a test. So I'll put the battery in there. Pin 18 is this one right here. That is the VCC for the chip. And if we go to the ground pin right here, oh, you can't see what I'm doing. So move this closer. There it is. So let's do that again. Pin 18, and we're going to go to ground. So there we go. We're getting 3.2 whatever volts on the battery right now. Now, if we don't go through the diode, oh, it's roughly the same. But that's because there's no voltage drop of any kind right now happening across the battery connection to this chip. If we pop the battery out and we switch this into diode mode, let's see here. So this is the Schottky diode. There it is. There's that voltage drop for the Schottky diode. And then when it comes to the actual 5 volts coming from the computer power supply, if I just get through the oxidation, there it is, 0.6 volt drop. So that means if we check for resistance between the battery and the 5 volts, well, it's in the mega ohm range, which is what we would expect with those diodes there. So as I said, the positive of this can feed the chip, and the positive of the power supply, that's coming right from 5 volts to that point right there, that can feed the chip as well, but the battery cannot feed the 5 volts on the entire board, and the 5 volts from this will not charge the battery. Now, one thing is when we go to turn this on, we will see 5 volts or some amount of voltage right here on this pin that goes to the positive side of the battery. And that's because there's some amount of leakage through Schottky diodes. That's okay though. It's such a tiny amount of current that when you actually have the battery in place, it's not actually gonna do anything. All right, so let's do a little bit of testing. On the 5 volt pin going to the chip, I expect when I turn this on, we should see like 4.7 volts or something like that, or something will burn. Let's see. Okay, 4.7, exactly what I thought. And over here, we should probably see, yep, we're gonna see 4.7, but don't worry, that's not actually gonna be charging the battery because like I said, that is such a small amount of current that is completely fine. Now what this also means that if we pop in the battery and the power is off right now, on pin 18, we're gonna start seeing 3 point whatever volts. Okay, well, it's this little cap here is actually charged up. So it'll drop down, there it goes. Well, when we turn this on, this should drop right back to 4.7 volts again. There it is. And we check over here on the positive side and see we're still at 3.2 volts. It's not charging that battery, not through that Schottky diode. But when we turn off the power, this will just slowly drop down to like 3 point whatever, which is the maintenance voltage from that battery to keep that chip alive. And there it goes. So let's take the battery out and let's put this chip in there. And we will see if this thing actually works at all. Because, you know, it's a big mystery if it's actually going to be working. First of all, let's just make sure when we power this on that we are going to have the correct voltage here at this chip. 4.5. That makes sense actually, because remember, 0.6 volt drop through this diode right here. It's a regular silicon diode. And let's turn this off and see how quickly it drops. Oh, very fast. I mean, this chip may not be in happy shape. Maybe it's shorted internally. Let's see if it was hot. No, it's not even warm or anything like that. Well, before I put the battery in, I think the best thing to do is power up this computer and boot into Workbench, and let's see if we can actually talk to the clock calendar at all. There could still be bad traces in this area. I mean, I did check everything and I didn't see anything bad in this area, but there might still be bad traces. And well, you know, the clock chip itself could be damaged from all the battery leakage that has happened to it. Okay, so the BlueSCSI is hooked up. I don't think I even need the floppy drive. I do have a mouse connected and the video is connected. So let's power this on. Hopefully the machine still functions. Yeah, I see blinky lights on the BlueSCSI. I wonder if it's looking for the floppy drive right now. Let's plug in the floppy drive because it wasn't really doing anything there. So we'll plug that in there. Okay, turn that back on. Yeah, I hear the floppy drive accessing. So I think it's sitting there trying to access the floppy drive and it was failing. So yeah, okay. I suppose we can go to time. I mean, I could set some clock stuff here and then reboot the system. In fact, let's just set it to May 25th, which is today's date. The year's wrong, and that is the time. Why doesn't the save button work? Is that because it can't talk to the clock chip? Okay, I forgot that here in sysinfo, we can see the clock and it says clock not found. Not good, not good at all. I can see all my caches are on, so that's working. I think everyone knows what this means. Because this thing is not showing up, we're gonna have to use the oscilloscope here to try to see if we have all the normal activity we expect on the address lines, the data lines, and the read-write pins. Okay, so pin 2, which actually is a chip select that it's using, that's that fail input, that actually needs to be high. So first let's check that. I gotta get my windows organized. That's low. Well, that's a bit of a problem right there. Chip's definitely not gonna work without chip select line pin 2 being high. And it is not high right now, it is low. So right there is our first problem. Pin 1, on the other hand, this needs to be low, and it is low. I think the adjust pin, if I recall, that's just tied to ground. Now let's check out the address line. So this is pin 4. That looks good. That's an address line. And that's the next address line, pin 1. Then that one is good. And that one is good. Okay, so the 3 address lines look good. We have a read line. And it is high right now, but it's active low. So that's fine. That's probably only when I try to read the clock does it actually show up. Pin 10, which is active low, is also just high right now, which is fine. That'll only be active while it's reading or writing to the chip. This is data line 0, pin 11, looks good. Data line 1 looks good. 2 looks good. 3 looks good. And then we have the oscillator pins. So this is 32 kilohertz. And there we go, 32 kilohertz. Okay, so the crystal is working properly. Our problem is this chip select line, pin 2. So what I want to do is I want to check this signal on other chips. But the problem is these PLCC chips like Gary, it's hard to do that. So is it going to any other through-hole chip? It doesn't look like it. It goes to Gary and it goes to Ramsey. Those two take that input. And then, of course, it's coming from this component. So where is this little PST518U118? It's a little 3-pin package. Okay, U112, I see it. It's right here. All right, so let's check out its outputs. The computer's off right now. You know what I can do? Let's actually start to see if we have continuity between one of the pins on this little package. It's near the power supply connector, which makes sense because it's checking the 5-volt signal, right? So we're looking specifically for pin 2 on the clock chip, going to any of those pins. And we'll switch my multimeter into the correct mode. I have a feeling we're just going to have to do a bodge wire here. Nope, that's obviously a bad connection because there's nothing going to any 3 of those pins. Okay. Okay, there's that little component right there. It's going to be hard to see, but that's the component. There's the resistor that goes to 5 volts. There's a capacitor. I think it's, I don't know where the capacitor is, but anyways, this is the pin 3 that goes over to our chip over here, our little clock chip, which of course is off camera. So let me slide this all over. There we go. And it's supposed to go to pin 2, which is right here. That is pin 2. Let's just double check. Yeah, there's definitely no connection there. So there's a break somewhere over here that I missed. Okay, well, I'm just going to put a bodge wire. There's a via right here that pin 2 goes to. That is connected. So it must be on the other side of the board because this via is right in the battery damage area. The battery damage area is right there. So that via comes up and it's supposed to go over to right here and it doesn't work. So just bodge wire time. It's the easiest thing to do. Okay, I have a bodge wire on there. It's green, so you can't really see it that well. But if we flip this back over, we should now have that connection that I so desire. So pin 2 on the clock chip should now go to pin 3 on the little component. And it does. Excellent. All right, let's power this up. Fingers crossed, nothing bad happens. It's funny, this black screen you get, oh, there we go, it's booting anyways. The black screen you get just, it's not reassuring at all, especially when you're dealing with machines that are sort of messing up like this one is. Sysinfo, let's go right to here, see if our clock is found. Clock found, yes, all right. Now let's go back to our preferences and I wanna check to see if I have the save button available. The save button is available now. That is awesome. All right, so what I'm gonna do is I'm gonna set the time appropriately. We're gonna hit save. I'm gonna need to put the battery in there. So May 25th, the year doesn't matter, and it's 2:26 p.m. And let's pop in the battery here. Okay, and turn off the system. And now we just wait. In fact, let's just check the voltage real quick on the chip, the clock chip, while it has the battery in the board. Because I'm curious to see what the load, what it's actually going to be. So the blue wires on the Amiga, by the way, are the ground rail. So pin 18, there we go, 3.15. So that's what the voltage drop of the diode, well above the 2.2 volts that this chip needs to run and keep the time. So it's keeping the time. I mean, we saw that the oscillator was good. This little adjustment here, it does allow you to fine tune the oscillator, but you need a really accurate frequency counter to get that dialed in perfectly. But I suppose if your clock drifts a lot, you can adjust that and just guess, turn it a little bit, see if it's a little bit better. One way will be worse, one way will be better. Okay, let's turn this thing back on and let's see if our clock retained its settings. So that was a success if, of course, it does retain the settings. Well, let's see what happens. Preferences, time, May 25th, 2:27 p.m. Yes, freaking worked. So there we go, that clock chip, even though it was bathed in so much battery juice over all that time, is still functional. So we have a working clock calendar on this Amiga 3000. Awesome. Okay, so another thing I want to test is the flicker fixer. And if we move the VGA cable for my capture device into the flicker fixer directly, let's look at what this looks like. It might flash, so yeah, sorry about that. Okay, so first off, we're getting a lot of waviness. and we're in bypass mode. So right now this shouldn't be wavy or any more wavy than it was in the when I was hooked up through the other connector here. Now if I flip the switch out of bypass mode, I know it's going to be all messed up. Oh yeah, that's very screwed up. Okay. Now here's the question. There are two adjustments for the flicker fixer. There's this little one down here, which seems to have sort of an effect, but it doesn't really come good. Okay, so there's that. And then there's also this one on the back, which I think is a phase control or something like that. Let's turn this one. I remember talking to James, who had this computer before me, and James said that he definitely fiddled with these controls. Doesn't really seem to do anything. I don't know if it has any effect only when you're in this mode. No, I don't know. And again, this little control right here, I mean, that has an effect, but it never comes completely good. There's also this jumper here. What does this do? Let's take it off. See if it does anything while the system is running. Seems to have no effect. Flip the switch. Oh, look at that. Interesting, it looks different. The jumper does have an effect, so in one position it's that, and in the other one, it's that. Okay, let's turn this control now. Oh, wow. Okay, so clearly this control is for the flicker fixer mode itself. Okay, what about this one on the back? See if this has any effect while we're in flicker fixer mode. Clearly it's not working well though. I mean, we obviously have a serious issue of some kind. I'm quite sure we're running in 31 kilohertz mode though. You know, unfortunately, one of the problems with my Extron here is there's really no way for me to see what the actual input frequency is. I don't think it has that anywhere on here. Yeah, I don't want to pick auto image. Yeah, there's not a whole lot of information on here. Auto image off, freeze off. Yeah, pretty useless when it comes to telling me what this is. I'm pretty sure we're looking at 31 kilohertz. The switch is in the down position, and when I flip to the up position, now it's in bypass mode, which is 15 kilohertz, and you know, it switched to the 15 kilohertz profile. But yeah, that's very, very wobbly. But I almost feel like, I mean, I know there's a bad trace in here, at least one. Maybe it's just, you know, we're getting this horrible jitter because of that. Let's switch this to interlaced mode. Wow, look how it's, yeah, very odd what it's doing. Let's switch to interlaced. Ah, okay. Sorry about the flicker, everyone. That's horrible. I wonder if this jumper does anything. Yeah, I don't know. I don't know what this jumper does. It obviously has some kind of an effect. That's what the flicker fixer enabled right now. So we should be in 31 kilohertz. Let me fiddle with this control just a little bit more. It seems to have a very dramatic effect. Very interesting. Wow, it's like weird. Like for a second there, it actually looks nearly perfect. Okay, well, I think I'm gonna turn this power off. I mean, I know there's a bad trace, so let me try to figure out which is the bad trace, and we're gonna bodge over that to restore that connection, and maybe this will just sort of start working a lot better with that trace fixed. Now, the bad trace is in this area right there between those chips. You see these two vias? Oh, no. See that via and this connection? I think it's this pin, which, what is this? U480. I guess we'll look up on the schematics what it is. So I think it's this pin, and I think it goes up somewhere up there. Okay, so I'm in continuity mode. There's the beeping. And we should get that signal up here. Oh, we do. Okay, so maybe the break is on this via. It's going to this chip. And this is like one of the frame buffer chips or something like that. Yeah, that's definitely broken. So you could see that via, if I touch the trace over here, okay, it's not even working there. So it works there, sort of dies somewhere around here. I think under that silkscreen writing it's broken, because it definitely is not there. But yeah, this one is okay. We can see it all the way up here. All right, so let's try to figure this out. So this is 470 or 475. This is 475, I think. This would be 470. Let's go to the schematics and look at pin 2. All right, so here's 470, pin 2, RSTW. That should make its way to 471 pin 2, 472 pin 2, and it makes its way over to the 74LS74 at U480 pin 5. Okay, so here's 480 pin 5. Okay, so yeah, that's connected to that via. and it's supposed to go to pin 2, which we know it's not working. And I think it should go to pin 2 on these other chips as well. Nope, it's not going there. And this one, nope, not going there. Okay, so that connection is broken to these other 3 chips, but pin 2 on all of these should be common together. Yes, it is. So what I can do on the bottom side is I'll just bodge pin 2 on this chip to pin, which one was it here? Pin 5. Pin 5 on that chip to pin 2 there, and that will connect up all those chips together. Okay, bodge wire installed, pin 5 up to pin 2. So when we take a look at pin 2 on these chips, should go this via now that it didn't used to, which goes to pin 5. So it's good there. It's good there. These pins are so corroded, and it's good there. Okay, I am still concerned about the fact that even on bypass mode, we're still getting a bunch of that weird jitter. That should obviously not be happening, but because I don't really understand how the amber chip works, maybe those chips are still necessary for operation, even in the bypass mode. Let's turn this on. Is everything good to go? Yep. Let's see what happens. And will we have a more stable image? No. There is absolutely no difference. So there's bypass mode, wobbly as all. And there's 31 kilohertz mode. Still not looking good either. Let's fiddle with these controls a little bit. No, this is still massively sensitive. What I'm going to do is I'm going to plug in a normal LCD monitor on my bench that only supports 31 kilohertz. I just want to see if it's even outputting 31 kilohertz at all. Oh, it is actually. So in the down position with the little adjustment adjusted the way it is, I do see an image. It's just as messed up as we saw with like the weird combing effect. But in the up position, the monitor says out of range. Sorry, you can't see it. So what you're looking at there is, without a doubt, actually 31 kilohertz. Let's flip that jumper back to the other position. Let me adjust this control again. See if I can dial this in a bit better. Okay. Well, does that look better than anything we've ever seen before? Yes? Maybe? Still a little bit of jitter? The control is so sensitive. I can't imagine this is how it's supposed to be. It is unbelievably sensitive. You just turn that like tiny fraction in it, it goes completely wild. I'm also not convinced it's going to work in interlaced mode either. Oh, well, let's give that a try. Let's try changing the screen mode. I mean, this is sort of working the way it was working before I fixed that bad trace. Interlaced? No. I mean, if anything, what we're looking at here is that it is deinterlacing, but I think we might have like a bad, one of these chips is just bad. That would sort of explain what we're seeing here. Non-interlaced, generally working. Now, of course, I'm capturing this image from my Extron. It doesn't do a great job compared to, say, an analog monitor. This is designed to output to an analog monitor. The digitization process, if it's not, synchronized exactly to the phase and everything, you're going to get a little bit of jitter like that. That's completely normal. I have a feeling if I hooked up an analog CRT VGA monitor, it probably would look fine in this non-interlaced mode. Without a doubt, interlaced is broken though. And that's probably got to be one of these chips here that's causing that. I need to install PAL so we can take a look at this in 50 hertz. So all we need to do is move this into here, and I will need to reboot the computer. I had it off for a while I was fixing those bodges. Let's just check the time real quick. May 25th, 2:50, right on the money. That's awesome. That actually works. Okay, so let's reboot. All right, so rebooting this thing, I'm going to see if PAL looks okay through the flicker fixer, which is what we're looking at here. Wow, what was that weird error? Weird. I didn't even catch it. Now that I put that monitor in there for PAL, we should have PAL available. So let's see if this works. Yeah, it works. Cool. And I think my Extron is causing it to be shifted over to the side, but obviously it's working. What's really surprising to me is there seems to be no difference at all having fixed that wire. Although maybe there is a difference because I can actually, get that dialed in, and I couldn't seem to dial it in before. I wanted to take a look back at the flicker fixer though. Let's see what these various switches and various controls on here do, according to this at least. This is the toggle switch on the back of the computer. That one works. Then there's this scan doubler C-Sync. That's that jumper I'm pretty sure I was changing. Now I'm looking for that little adjustable capacitor. Oh, here it is right there. VC470. So it has to do with the clock that's probably fed into Amber. Oh, we have another jumper for open and closed loop. That might have been the jumper that I was changing, actually, because I see another couple jumpers right near Amber. That might have been the other one. So 482, the labeling on the board is not clear as to what jumper that is, actually. It'd make much more sense that the jumper I was changing was this one, actually, because it does say open and close on there. So it must be something to do with the phase loop lock or something. Right now, it is in the close loop position. So the gain connection goes through this resistor back to the VCC through those components there. And then as for the little control on the back of the computer, the VR470, that's got to be this, the phase adjust, which really doesn't seem to have any visible effect, but maybe we need a better test pattern to adjust that properly. I'm just kind of thinking here for a second. The one thing I haven't done is take Amber out of the board and deoxit that socket, because all the other chips got that treatment. And if any kind of gunk went up here, then it's quite possible that we got some dirty stuff in there. Wow, Amber is positively stuck in the socket. Normally you can kind of pry it out a little bit with something like a pick. That's not really working. I don't want to break the socket. And for whatever reason, I can't get this tool into that side. These have little hooks on them. It's supposed to go under the PLCC chip so you can hook it out. But it needs to get under the chip on both sides. And I cannot get it under that one at all. Okay, I got the chip out. I think what was going on is it's just the pins were really oxidized. But it's out, and the socket's not broken, so that's good. I brushed the legs of the chip with a little fiberglass brush, and in goes deoxit. And we're going to put that chip back in, and we're going to hope that there's a difference. It's quite possible that one of these frame buffer chips are damaged just because of the corrosion can break the hermetic seal. Amber's a little bit worse for wear with some scratches. But there it is, back in the socket. Pin 1, there's a dot right there, and there's a 1 printed on the PCB there, so I know it's in the correct way. All right, here we go. Let's see what happens. System is powered up. Are we going to have a working image or not? Okay. That's weird. What? I'll have to look at that in editing. I couldn't even read what that said. All right, so our big test is going to interlaced mode. No difference. And I just hooked up my LCD monitor, and in 240p mode or non-interlaced mode, it looks perfect. No issues whatsoever. In fact, all the little jitter we saw through the capture device is not even visible on this LCD screen. And this is not even a CRT. It looks perfect. Yeah, I don't see a single pixel out of place. But when I go to interlaced mode, the corruption is identical to what we're seeing through the capture device. So either the Amber chip itself is bad, which is probably not likely. I mean, it's possible, right? More likely is one of those frame buffer chips is bad or not hooked up properly. So I think that type of troubleshooting will be too much for this video. So because I'm trying to keep the video lengths from being too long, I think I'm going to have to put the repair of the flicker fixer into the next video for the Amiga 3000. Plus, that will give people time to comment on this video to let me know what they think is the problem with the flicker fixer. I'm also going to put some questions out there to ask people what it means when it's corrupted in interlaced mode, but non-interlaced mode looks perfect, because that's the exact symptoms we have now. So yeah, we either have bad traces, bad Amber chip, or we have a bad frame buffer chip, one of those special chips in here that does the frame buffering. All right, so I think that's going to be it for this video. I'm glad to have at least made some forward progress here. Clock calendar is now working. Flicker fixer is kind of working, just not in interlaced mode, which of course is the whole point of the flicker fixer. And then finally, I now fully understand what it takes to make this Amiga work without the riser installed, which is how it is right now. Booting Kickstart 3.1, running Workbench 3.04. You don't need this thing installed to do that because of the patched ROM. And like I said, there'll be a link in the description to the Python script if you want to modify one of the Kickstart ROMs. I assume it will work with any of the Amiga 3000 ones that have this problem. So in the future, if you're doing troubleshooting like I am with the flicker fixer, it's just nicer not to have this thing installed, being in the way while you're doing the troubleshooting. And when it comes to the Amiga Mon diagnostic ROM itself, not quite ready to release that yet. Don't worry though, it will happen. I just need to do some more troubleshooting and work on it, probably off camera, and maybe I'll make a second channel video where I kind of show off the features of it and then stick it up on GitHub. It's not going to be anything close to feature complete compared to the other diagnostic ROMs that are out there, because this has been tested on exactly one Amiga, this one plus UAE, and we already know that the UAE emulator is just not accurate when it comes to hardware side effects. Like UAE is really designed to simulate the hardware to the point where all the software will work. It just doesn't need to even bother to emulate all the weird edge cases like bus errors and stuff like that, because none of that is normal operation for an Amiga. So it doesn't emulate that stuff. And therefore it makes it really hard to test diagnostic ROMs with it, other than you can just make sure it boots up and, you know, seems to say everything is working. But simulating RAM errors or bus errors or any other weird problems that you can actually have on Amigas, you can't really do that with the emulators. You got to do it on real hardware. So I need to do more testing, and it's just time, essence, all those things, you know, the usual stuff. Anyhow, I hope you enjoyed this video. If you did, thumbs up. Definitely comment down below. I'd love to hear what people think about this whole patching the Kickstart stuff and whatnot. And I guess that's going to be that. So I think when this goes live, I will be at VCF in Dallas. So maybe I'll be seeing some of you there. Otherwise, I will see you on the next video. So stay healthy, stay safe. I'll see you next time. Bye.